is CENTEXBEL, who will talk about the manufacture of braided reinforcement-based composites and their mechanical performances.
So good afternoon, everybody. So I'm Baptiste Erlin from CENTEXBEL. CENTEXBEL is a research technical center based in Belgium and specialized in technical textile. So we are working more especially on medical device, technical textile, and also composite application. So my talk is more focused on the work done to produce composite materials and to test them during the COBRACOMP project. Colleagues have already explained in the previous presentation. The start of the project comes from an existing patent of braiding technology, so from George Cahuzac patent. And the main goal of this project is to develop and build this machine and test the braiding materials on a use case proposed by Euramaterials, which is an aeronautic blades. So few words about aeronautic blades production. That it's already done by Euramaterials. So you can hear on this dia the spare part overbraided on a polyurethane foam mandrel. And to produce the blades, a layup requirement is 0 degree, so unidirectional, and also plus and minus braid angle for the bias direction. Depending the final use of the blade, the size and the number of blades used for the plane, plus and minus angle and unidirectional plies are braided in a sequence defined by the designs. So that means they need to use two machines to perform this textile reinforcement. And for some more applications, some unidirectional fabric are added by hand. So here a few words about the high quality braid specification for the next generation of blade. So what is the need? We have to minimize the braid thickness of the HQ braid compared to the Ratier-Figeac standards. Why? It's because the starting point is classic braiding reinforcement. That means a monolayer braid, and we will produce a 2-layer braid with interlock. That means the thickness will be bigger than the classic braid. So, but we have to minimize the difference between the two thickness. But thanks to the new yarn position and movement, the thickness variation of the new high quality braid will be minimized. So as Stefan has already explained, here you can see some curvature of the yarn braid, and thanks to the HQ braid, this variation will be less compared to the classic braid structure. The fiber volume rate reach will be the same, so 58%, and the UD ratio will be from 42 to 45%. We have also to play with the cover factor of the braid because this braid reinforcements will be injected in a mold, and we have to close this mold, but we cannot apply too much pressure on this mold because of the mechanical resistance of the spare foam. So that means the cover factor has to be adapted to apply a maximum of pressure of 5 bars during the close molding. The braid angles is fixed at plus and minus 45 with unidirectional yarns too. And at last, we have to minimize the braid detachment from mandrel due to perimeter reduction. But of course, before to develop and build the new machine, it is necessary to study and compare existing braid materials. So yeah, before to build the new machine, we have to compare the benchmark of braiding technologies. That means we will test existing braid machine which is a standard triaxial monolayer braid machine and also a multi-layer interlock braiding machine. So we work with existing, I admit, Kevin. So we work on existing braiding machine from Eurocarbon and CENTEXBEL. So to, yeah. Okay, sorry. I heard somebody to talk. Yeah, we have to fix different kind of parameters to test and compare the different kind of materials. So we will work on the baseline, which is made by Ratier-Figeac, and we compare the triaxial monolayer braid from Eurocarbon and multi-layer interlock braid from CENTEXBEL. Ratier-Figeac fixed the material use for carbon materials and also some parameters like UD fraction and also the thickness of the composite plate. And partners who are using braiding technology have to adapt their machine to produce braid reinforcement, which can be used in the mold of co-expert for the RTM process. When Eurocarbon and CENTEXBEL have produced this mechanical, this textile reinforcement, we have to send this semi-finished materials to co-expert to make the RTM process to obtain the composite plates used for mechanical test and in static and fatigue way. So here you can see some kind of mechanical performances we want to have. So the modulus, the static tensile, fatigue resistance, G2C and G1C for damage tolerance, for examples. Here it's just a summary of some static tests, so I will pass quickly. Now I will present you all the configuration of textile used for produce composite plates. So the baseline proposed by Ratier-Figeac is made by a superposition of biaxial braid and 3 unidirectional woven with another braid and 3 more unidirectional woven, and to finish with a braid ply. The braid part is done with a braiding machine using 144 carriers, and the unidirectional woven is a TPI from Excel with IM7 glass carbon fibers used. So the fiber volume is 58% with a UD percentage of 44%. For the triaxial braid, so Eurocarbon used 1 yarn of 6K in the bias direction with 144 carriers, and fill with 2 yarns per position of unidirectional yarns. And for the CENTEXBEL configuration, we use 2 yarns per bobbins, so with a total bobbins of 256 bobbins, and 2 yarns of unidirectional yarns too. So here on this tier, you can have a look on the existing machine used during the project to produce the composite, the benchmark composite materials. So at left, just here, you can see the monolayer axial braiding machine used in at Eurocarbon. And at right, you can have a look on the multi-layer interlock braiding machine used at CENTEXBEL. So for the monolayer machine, so it is used with 144 bobbins and 72 position for UD yarns, And for the multi-layer interlock braiding machine, we use 256 bobbin and the same quantity of unidirectional yarns. So normally in this project, it was planned to modify this machine to increase the quantity of unidirectional yarns we can fill in the braid reinforcement, but this step has been cancelled. So we only work with this existing machine without modification. So we have already seen this drawing, but here you can see the position of bias yarn and UD yarns. And we see the same with with the multi-layer braiding machine. So here you can see the 4 layers of UD yarns and also all the movements of bias yarn. So here you can see, for example, maybe a bright color. Yeah, here the red one, which will link the second UD yarns with the third UD yarns to create the interlock. Of course, the thickness of the braid produced by multi-layer interlock braiding machine is bigger than the mono-layer braiding, but we have also more waviness, more wave, more curve, sorry, for the bias yarns, which can have some consequences on the mechanical properties. Yeah, very quickly on this dia, because yeah, we have already seen a lot of things about the new machine, but here it's a view of the high-quality braid machine with a 6-axis robot used to handle the mandrel. So here you can see the 2-layer interlock and also all the position of UD yarns. Yeah, as my colleague have already explained, normally this configuration will minimize the thickness variation and also increase drastically the percentage of UD yarns that will bring more mechanical performances. So after several meetings between us to discuss about the minimum UD ratio or the maximum braid thickness we can achieve for multi-layer interlock braids or monolayer triaxial braids. Some braiding parameters are fixed. So we fixed 3 types of braid angles, so 35, 45, and 55 braid angles. And Eurocarbon and CENTEXBEL have to adapt the size of the mandrel to keep the thickness and the surface weight constant, so to compare the future composite plate. The braids are done on a circular mandrel to obtain an homogeneous yarn placement, and they were cut to be used on a flat direction and injected by co-expert partners. Few words about the RTM injection. So it's made by using RTM6 resins with a temperature of injection of 120 degrees, and it is a post-cure at 180 degrees during 2 hours. Okay, so after the cure steps, we made some visual control to check that the composite plate is good. And after that, all these plates have to be cut following the testing plan. Why? Because in fact, each standard test needs to be normalized. Sorry. yes, all the coupons have to be normalized. Yeah, and the better way to achieve this is to use waterjet cutting. So this step is not done by the partnership; it's subcontracted. After that, we test mechanical performances in a static way using a benchmark test equipped with a 100 kilonewton load cell. And we have to prepare, of course, all the coupon tests. For example, for the failure stress, we have to glue some glass tabs to avoid the damage of the carbon composite in the clumps of the machine. And we also apply different strain gauges on each side to measure the G12 modulus. So here it's just to have a look. I will not speak a lot on this table. It's all the summarized table tests when you can see the failure stress result modulus for each series. So for baseline, Eurocarbon, and CENTEXBEL braid composite plate. Yeah, depending the braid angles and also the test orientation. So here in axial direction and also in transversal direction. So the first one is for the baseline materials, then for the CENTEXBEL plate, and to the end the Eurocarbon plate. Yes. Oops. Sorry. Now some word about test results. Here you can see a table with the UD percentage depending the braid angles from each configuration. And the first graph speak about modulus of the coupon test in axial direction. So you can see that for the rigidity of the coupon are closed at 35 and 45 degrees. But we can see that at 55 UD fabrics and biaxial braid, so the baseline materials, bring better results if you compare with the triaxial monolayer and multi-layer braid. So yeah, it can be explained by the UD ratio, see on the table here, which is lower for the braid structures, and also maybe by the waviness of UD and BS yarn. Yeah, for the failure stress, yeah, you can, yeah, we can see that the baseline obtains a higher results compared with the braid structures. Yeah, we can also conclude that it's maybe due to the waviness of UD yarns and also BS yarns. No, the same test, but in the transverse direction. That means the coupons are cut perpendicularly at the UD yarn direction. That explains the decreasing of the value compared with the axial direction. But in transverse direction, mechanical performances is brought by the bias yarn. And we can see that, yeah, interlock structure seems to lead more mechanical resistance at 45 degrees compared with the baseline and classic triaxial samples. But yeah, unfortunately, this result is not really correlated with the result at 55 degrees. So for the failure stress in the transverse direction, yeah, the multi-layer interlock references reach close to the baseline at 35 degrees and obtain, yeah, better results at 45 and 55 degrees. So maybe the linkage of Biasians could bring improvement of behavior. For the G12 modulus, yeah, what we can see about that. For the modulus, it's quite comparable with three structures. And yeah, concerning the failure stress, yeah, interlock braid reach value more close to the baseline compared with the monoaxial configuration. Yeah, so no, after the classic static test, we perform also some fatigue test. Yeah, I will try to summarize them quickly. So on this graph, we can see here the static result of baseline, yeah, in orange, baseline, and also monolayer triaxial braid materials. And yeah, what we can see if we compare the static results with the fatigue results, is that fatigue test sorry, fatigue life limits the knockdown with triaxial braids, but it's mainly due to the UD waviness and also the UD ratio. So the same conclusion than a static test. Now, few words about damage tolerance. Sorry. So with the static G1C and G2C test, so the G1C with a double cantilever beam and the G2C for the end notch flexion. Yeah, what we can see with the graph here is that we can show some unstable crack propagation, and the composites reach a value of 992 megapascal, but with a high dispersion in the results, as we can see with the high value of the coefficient of variation. Sorry. If we compare the result with the monolayer braid structures, we can see that the cracks are less unstable compared to the baseline, and we also obtain a better repeatability. We have a loss of approximately 10% of the value compared to the baseline. For the G2C results, nope, I think I pass. Oh, sorry, I put yeah, normally it's first this one. Yeah, sorry. Yeah, for the baseline, we reach a value close to 1000 megapascal, and if we compare the G2C results of the braid samples, it is 39% better compared with the baseline, and we obtain this result with a good repeatability. So in conclusion, with this axial fatigue test is lower on the braid structures, but with a new configuration where the two parameters involved in the decrease of performances, which are UD percentage and also waviness of the yarns. The decrease of the waviness of the yarns, it could be yeah, the result should be better with a new HQ braiding machine. For damage tolerance, so G1C and G2C, the result is close to the baseline or better. Yeah, it seems that the braid structure limits the crack propagation, sorry. And for G2C, braid structure reach the better result. So it's a good result for the project. Yep. Okay, now very quickly, some word about the demonstrator design and also the machine design, because it stays more in theory than in a practical way. Yeah, so what we want to achieve it's to check that the high quality braid behavior and limits in situ. That means braid angle and thickness distribution. Cover factor is okay for the blade module. We have also to verify the braid simulation, compare with the experimental test. Of course, check the injection quality and verify the blade root structural capacity. That means mainly partners which are Eurocarbon with a Collins support for the braiding part. In parallel, the braiding simulation have to be done by University of Twente. And at the end, of course, Collins will inject and test the demonstrator. Yeah, few words about the machine, because we have already a lot of information about this. So you can see that it's 2 rows of 36 wheels and 5 notches per wheels for a total of 180 bobbins. So here we have all the need for the high quality architecture. So the percentage of UD, the number of yarns, the type of yarns, and also braid thickness prediction. So to conclude this presentation, yeah, I've already said a lot of, so I will maybe go quickly. Yeah, the mechanical properties of triaxial braids in state-of-art configuration has been compared to Ratchet-Figeac baseline made with UD and biaxial braid. So what we have seen with this test, it's that tensile fatigue test is not done with a triaxial braid due to mainly with UD and bias waveness, and also the UD percentage, which is lower than the baseline. For damage tolerance, we achieve comparable value and better value with the braid structure, so which is a good result. And for the blade demonstrator, yeah, different kind of thing have been defined, but we cannot do all the stuff on this task. So it's mainly theoretical point of view compare experimental work. So thank you. And if you have some question, don't hesitate.